Hello everyone and welcome back. So last class we were discussing about the contact resistance significance, and we discussed that by employing a good surface or good quality surface, good polished surface between GDL, that is gas diffusion layer, and the bipolar plate, we can minimize the contact resistance because the surface interaction between these two components will increase. There will be more pathways for electrons to flow across this interface, and we can bring down this contact resistance. We also discussed that this in case of fuel cells electrolyzers, which are typically clamped together using these nuts and bolts, and since they are clamped or these nuts and bolts are clamped at the extreme ends of the plates, we can see that for a smaller cells there is a good clamping that is observed for us cells or the stacks having areas, effective area less than 50 centimeter square or so. However, if the contact area, if the area of the cell increases, then there is a local bending that is observed between these bipolar plates, and that leads to higher contact resistance. And we can see that in case of poor contact between gas diffusion layer and bipolar plate, this contact resistance will increase. So in order to minimize this contact resistance, we should definitely have a good contact between diffusion layer and bipolar plate, and for that we need to have a good contact pressure at the interface of this GDL and bipolar plate. And typically in case of planar structures, roughly 1 megapascal of contact pressure is considered to be of good quantity. So in other words, let us say if I have this is my area of the electrode. So this is my area of the electrode. So if I look at, from the side view, this is my electrolyte, and this is my GDL or the electrode. So my bipolar plate will be something like this. So I am talking about the contact pressure at these points here. So contact pressure here should be around 1 megapascal, which is at the interface of bipolar plate and the GDL. This is my GDL. So to summarize, first you have the electrolyte, should have high ionic conductivity, as we have seen that this ohmic resistance is directly proportional to the length and it is inversely proportional to the ionic conductivity. So if the ionic conductivity is good, the ohmic resistance will be less. At the same time, this electrolyte should have very low electrical conductivity to avoid electrical shorting. Now what does this mean to? So if I have, this is let us say a fuel cell, and we know that these electrons are basically, they travel from anode to cathode. These are the electrons and this is the protons theoretically. So, if this electrolyte is having a good electrical conductivity as well, so instead of these electrons traveling in the external circuit, they will travel through the electrolyte, and in that way we will not be able to get any electricity or any flow of electrons in the external circuit, and that is why this will ultimately lead to electrical shorting. So, why this happens? Because there is no potential difference will be there. So, it will be almost 0, and that is why the electrons will straight away flow from anode to cathode instead of flowing from the external circuit. So, that implies no flow of electrons in the external circuit. Third is electrolyte should have very low fuel crossover. So, that implies it should have sufficient thickness, as we have seen that if the thickness of the electrolyte is enough, then there is very low probability of fuel getting crossed from anode to the cathode. And fourth one is it should have electrolyte should have good mechanical strength, and fifth one is should have good contact between gas diffusion layer and bipolar plate, as we have seen that this good contact between gas diffusion layer and bipolar plate leads to lower contact resistance. So, let us move on to the other points. So, this gas diffusion layer, in order to have a lower contact resistance, should have microporous layer as well. So, it is preferred. Since if we have the microporous layer on the gas diffusion layer, we have seen that the surface roughness of this GDL gets reduced drastically. Same thing is also applicable for the bipolar plate. So, let me write bipolar plate should have good electrical conductivity first, and this surface roughness of bipolar plate should be low. So, low means preferably below 5 microns or so. So, this can be employed by using good anti-corrosive coatings, which once they are coated on the surface of bipolar plate, the roughness of the bipolar plate also comes down, and it also offers a good electrical conductivity or the contact points between gas diffusion layer and the bipolar plate. So, let me write that. So, this bipolar plate to have good coatings. So, there are many anti-corrosive coatings. We can go for titanium nitride coating, or we can also go for chromium nitride. There are literature available in the that underline the coating of platinum or gold as well. So, these anti-corrosive coatings basically increase the life of bipolar plate. At the same time, they also reduce the roughness of the bipolar plate, and that basically increases the pathways for electrons to flow across the interface, and that is why it's preferred to have these anti-corrosive coatings. So that summarizes the various ways through which we can reduce the ohmic resistance in the fuel cell or in the case of electrolyzers. Let's move on to the other chapter, that is mass transport. So far what we have seen in case of this a fuel cell or electrolyzer, this is the zone of activation over potential, this is ohmic, and this is mass transport. Same is also applicable for the electrolyzer. This is E. So here also we have activation zone, mass transport, and we have seen that activation over potential is basically the energy invested in swiftly taking this electron from the chemisoft hydrogen. So if you remember the reaction, it is M dot H, which means hydrogen chemisoft on metal nanoparticle basically undergoes this reaction H plus, which is again near electrode. We have seen this reaction before. So this is for the fuel cell. We can similarly write for the electrolyzer. It is the energy invested in swiftly transferring electron to the H plus near electrode. This is in case of electrolyzer. Let me write this one for fuel cell. So it's a reverse reaction that we can think about in case of electrolyzers. Near electrode, which ultimately converts into chemisoft hydrogen. And in case of ohmic resistance, we have seen that it is I times R ohmic, which can also be written as I times. So we have to let's expand this ohmic resistance, which is sum of R ionic plus contact resistance and plus electrical resistance of individual components, and we know that ionic resistance is nothing but L by sigma A. So in other words, so we discussed about how electron and proton are basically conducted in respective metal and ionic conductors. In other words, the activation over potential talks about how electrons are basically swiftly taken from the metal nanoparticle on which the hydrogen is chemisoft, and that is all about the activation over potential. in coming to ohmic overpotential, we have seen that how this protons as well as electrons move through the external circuits as well as through the different components. So, this is all about the first two resistances or the first two overpotentials. Now, when we talk about the mass spaces, that is hydrogen and oxygen, when they are supplied to the fuel cell or when water is supplied to the electrolyzers, how this supply is basically hindered by resistance, or is there any resistance? So, answer is very yes, there is a resistance. It is not that simple as it appears to be. So, let us write that down. However, when we supply mass species, that is H2 and O2, say this is in case of fuel cell, or water in case of electrolysis, things become complicated than they appear. So, therefore, this mass transport loss which we will be denoting as eta mt is nothing but the energy lost. So, when we say energy lost, this is the in case of fuel cell, or the energy to be supplied in case of electrolysis while transporting the reactant and product basis to or from the electrode or a given rate of supply. In other words, this mass transport overpotential or mass transport loss is basically an energy lost while we transfer these reactant species, that is H2 and O2, and take this water out from the fuel cell, or when we supply water to the electrolyzer and take hydrogen and oxygen out in while this reaction happen at the respective electrodes. So, what is the energy invested? What is the excess energy that we have to supply in order to make this reactant species available at the reaction sites, and that is the energy is nothing but the mass transport loss. So, although it appears very simple, it is not. So, let us understand why it is so important. So, significance of eta mass transfer or overall the species that are basically made available at the reaction sites. So, let us understand this. So, this is anode and cathode. Let us take fuel cell as an example, and we supply hydrogen and oxygen. So, we know very well that reaction takes place at the triple phase boundary or at the catalyst layer, which is exactly at the interface of anode and electrolyte as well as the cathode and the electrolyte. So, this is where the all reactions are supposed to take place, anodic reaction and the cathodic reaction. So, let me write that down. The fuel cell performance depends highly on the concentration of hydrogen and oxygen, this is important, at the catalyst layer. At the catalyst layer, and not what is available or supplied in the channels of bipolar plate. So, in other words, let us say we are supplying some concentrations of hydrogen and oxygen at the in the bipolar plate. So, that is not important. What is important is what is available at the catalyst sites, or what is available at the catalyst layer, both at anode as well as cathode. That is what defines the performance of the fuel cell. Same thing is also applicable in case of electrolyzer. So, let us take this. This is let us say anode, and this is where we supplied water. So, we know that this is in case of PEM based fuel cell or PEM based electrolyzer. We know that the anodic reaction is basically splitting of water into protons and respective oxygen. So, we know that H2 gets produced on the cathode side. So, basically all these reactions are again taking place at the catalyst layer, respective catalyst layer. So, in other words, water, if it is available or it is made available in bulk quantity at the catalyst layer, then and then only the water splitting reaction will take place in the case of electrolyzer. So, this is for the electrolyzer, and this is the fuel cell. So, by measuring what is the water available at the catalyst site will define the performance of the electrolyzer. Similarly, what is the concentration available of hydrogen and oxygen at the catalyst layer will define the fuel cell performance. So, why is it so complicated? Therefore, it becomes very important that sufficient quantities of hydrogen and oxygen are made available at the reaction sites, so that what happens if the fuel cell is not supplied with enough quantity of this hydrogen oxygen, it basically leads to fuel cell starvation. So, that the fuel cell does not starve. So, how this can be minimized? How this problem can be minimized? How it can be so therefore, by incorporating better flow field designs. We have come across this flow field designs before when we saw the actual fuel cell, wherein we saw the monopore plate having channels. So, those channels are nothing but the flow field designs, and there are different designs available in the market. We will see those details of those flow field designs in upcoming sessions. So, by employing this better flow field designs, we can distribute. So, let me write that designs which will distribute the gases uniformly. This is important, uniformly over the electrode area. So, what it basically means is, let us say we have this electrode, this is the area. Now, theoretically all these reaction sites, these are the reaction sites, they are infinite reaction sites, or not infinite, at least there are many reaction sites, because all these reaction sites are nothing but the catalyst nanoparticles that are present, and all these reaction sites, if they receive the gases, then only there is a possibility of having those reactions possible at the respective reaction sites, and that is why it is very important to make sure that these gases reach each and every corner of the electrode, and that is possible only when we supply or we employ a good flow field designs. So, this is my flow field design. Let me draw on the top of this. So, this is one design that we saw. So, by employing a good flow field designs, we can ensure that all these reaction sites are, they are reached, and the reactions will take place then afterwards. So, let us understand what happens at the interface orbit and the bipolar plate and the diffusion layer, and what happens when the gas flows through those channels. So, let us take this diagram again. This is our electrolyte, and this is the gas diffusion layer. Now, we know that we have this bipolar plate channels. This is the catalyst layer. This is the gas diffusion layer. And this is where your hydrogen comes. So, this is the channels, and these are the ribs. So, if I try to zoom in here, this much portion, I can see that. So, there is a flow channel. This is my flow channel, and there is a diffusion layer here. And then we have a catalyst layer. So, we have hydrogen flowing through these channels. So, there is a convective transfer through convection, and we have this hydrogen flowing through the diffusion layer. And here it gets converted into protons. This is your bulk of electrolyte. So, if I show this phenomena with respect to concentration, this is the concentration. Let me write, this is the catalyst layer, this is electrolyte, this is GDL, and this is bipolar plate, and I mean to say this is the triple phase boundary. Catalyst layer is nothing but triple phase boundary. And so, let us draw these lines So, what is happening is this is the concentration of hydrogen, it is the bulk concentration, and as and when it enters, or as and when this hydrogen enters the diffusion layer through diffusion, the concentration will decrease because we are drawing some current. So, this is the concentration that is available at the interface at a given time. We have come across this term before. Let us call this as C star H2. Same is the case. Let me complete this. This is your flow channel, and this is the flow, and then we have this is the electrolyte, this is the flow. Let me write here, this is the flow in is due to diffusion. Okay. Since hydrogen diffuses through this diffusion layer, so the mode of travel of this hydrogen gas is through diffusion, and this is what is called as diffusion layer. And as we know, this is the electrolyte. So, this is basically distance. So, flow through this through the channel is due to convection. The convection can be natural convection or the forced convection. Natural convection means the fuel cell is, let us say, air breathing cell, wherein there is no external source of energy that we have employed to basically make this hydrogen flow through these channels. Same is the case with case of hydrogen, oxygen as well. And if there is a pump that is employed for making this hydrogen flow through this channel, then that becomes the forced convection. Same is also case available or applicable in case of oxygen. So, we will take on with this mass transport and how this happens in case of flow channels as well as diffusion layer in the upcoming sessions. Thank you.